Some of my favorite projects made by Cinema 4D artists are those that use fields. So today we'll create the same effect in Blender with geometry nodes, then apply it to a weight map that can be used on any function that supports limitations with vertex groups. In this tutorial, we'll focus mostly on pinning cloth simulations, but I'll include a couple of examples that aren't cloth simulations at the end of the video. We'll create 3 field types: linear, spherical, and random. But first, let's make the object. Since I'm inflating the object gradually, I'll create a multifaceted object rather than something overly generic. For that, I'm starting with an icosphere with 1 level of subdivisions, which I'll then extrude in edit mode using the extrude individual tool. I'll add a subdivision surface modifier to smooth everything, but to keep the edges relatively sharp, I'll also add a bevel modifier before the subdivision surface modifier. Finally, right-click the object and choose the smooth shading option. The arrangement of these modifiers will affect how our geometry nodes setup behaves. Subdivision means more points to work with in geometry nodes. Next, we'll create the field controllers, so let's just add an empty. I chose the sphere option so I can see it better. Although linear seems like a simple solution, you have to think about 3 dimensions or a combination of multiple. We'll start with 1 dimension, then apply the same logic to the rest. For now, let's start with the x-axis. While your object is selected, open the Geometry Nodes tab and add a new Geometry Nodes tree. Since we have a controller that determines the selection of the vertices per the controller's location, we need the Object Info node to get the empty's location. Select the empty in the Object dropdown, then select its X location through a separate XYZ node, since we're focusing on the X-axis. To figure out which vertices are passed by the empty, we need to compare the X location of the empty with the X location of each vertex on the object. Let's start with the general location of the object, then deal with the vertices. The reason I do this is to make sure the initial location of the object is accounted for. So we need another object info node, but now instead of hard-coding the object, pull a link out of the object socket and choose the self-object node. This ensures your geometry nodes tree applies to any other objects. Add a separate XYZ because, again, we're focusing on the x-axis, and finally connect the empty's X location to the first socket of a greater than compare node, and the object's X location to the second socket. Let's pin the geometry nodes tree so we can select the empty and move it to see the result we get if the empty's X location exceeds the object's X location. And to actually see the results, we need a viewer node. To add that, either use Shift-A and search for the node, or Shift-Control and mouse click on the node you want to view. Connect your geometry input to the geometry socket and the greater than result to the value socket. Our object will become solid black, but as soon as we move the empty to the right past the object's origin, it turns into solid white. This is already great, but now we need to control each vertex, so let's add the position of each point on the mesh to the initial location. Add a position node and use the add operation on the vector math node to combine the position and location values. Then input that into the separate XYZ node. You'll see that the resulting line changed from solid to dashes. That's because it's multiple values now rather than 1 location. Since the position node is reading the location of every point on the mesh, and if we turn on the viewer node by clicking the closed eye on it, we'll immediately see that the object now has 2 halves. One is white and the other is black. Whatever point is on the left of the empty, as in the empty is greater in value, will turn into white, and whatever is on the empty's right is black because it didn't meet the greater than condition. Time to apply the result to a vertex group or weight map so we can use it with the cloth modifier later. To do that, we need a vertex group, so let's add an empty one called pin to the Object Data Properties tab on the right under the vertex groups toggle. In the Geometry Nodes editor, pull a link from the result of the greater than node to the empty circle of the GeoNodes group output. Toggle on the side panel using the N key on your keyboard while hovering over the Geometry Nodes tab. This will give you the settings of whatever node you've selected. Select the group output node so we can edit the result properties name. Double-click the result property and rename it to vertex group and change its type to float. This will make it ready for the value that we're going to give it to. On the Modifiers tab, toggle the Output Attributes section and select the Pin Vertex group from the drop-down menu. If you switch to Weight Paint mode, you should have an object that is half red and half blue. Red is fully pinned and blue is the opposite when we use it with the cloth modifier. This already works if I add the cloth modifier. However, if you've selected some edges or points to pin previously, they will be overwritten by this new vertex group. So let's add the initial vertex group to whatever result we get from the geometry node setup. We'll start by adding a named attribute node with a default float type and selecting the pin group from the dropdown. Using a math node, add the greater than result to the pin group attribute and connect the value to the vertex group. In edit mode, select a few points or edges and assign them to the pin group. Now to check that everything is working, switch to the weight paint mode and you should see your added points as part of the pin group. Don't worry about what color is on which side, we'll fix that by adding a switch node that flips the values. To create this flip input, let's add a switch node of type Boolean. Link the switch socket to the empty circle on the group input, rename it to flip, and keep its type as Boolean. In the false socket, add the greater than result, and in the true socket, add a less than node result, and connect the same nodes you connected to the greater than A and B sockets to the A and B sockets of the less than node. The output of the switch node goes to the second value socket of the math node instead of the greater than node. This should switch the black and white values of the object. And if you turn on the viewer node, you should see the result by toggling the flip switch on the geometry nodes modifier. We have a perfectly working linear controller at the moment. Let's connect the y-axis instead of the x-axis while keeping the viewer node active. This should switch the linear gradient from a horizontal to a vertical transition. This means our example works with whatever axis. Let's make it better by making it dynamic. So let's add a menu switch to the modifier so the axis switch can happen with a click of a button. The data type should be a float, and the menu should be an input on the modifier. We should rename the input to access. To change the menu's values, select it and go to the Node tab on the GeoNodes editor's right side panel. If the side panel disappears for whatever reason, push the N key to retrieve it, and we'll always toggle it in and out. Double-click the A value and rename it to X, and change the B to Y, and then add a new value and change it to Z. Connect a separate XYZ node to the corresponding axes sockets on the menu switch node. Then connect its output to the A socket of the greater than node. This means our choice on the modifier tab will be reflected in the output. Turn the separate XYZ and menu switch into a group by selecting them and hitting Ctrl G. You should now be inside the new group. Add the vector socket as a group input. Now hit tab to get out of the group, rename the group to access switch. Next, connect the vector to the empty object's location and connect the access switch output to the A socket of the less than node. Then remove the old separate XYZ. Now duplicate the access switch group and connect the vector to the vector math node. Then connect its output to the V input of both the greater than and less than nodes. And make sure the access input is connected to the second access switch group as well. Turn on the viewer node and test out the new drop-down menu that appeared on your geometry nodes modifier. We can also add a diagonal line by combining the X and Y axes like so, and add it as an extra option in the drop-down menu. Let's fix one last thing before we move on to animation, and that's removing the hard-coded empty object and using an input instead. So when you decide to mark this node tree as an asset, Blender doesn't add an empty every time you import your asset into other files. Now add the object socket as an input and rename it to controller. And finally, select the empty as the controller in the modifier tab. It doesn't matter whether you choose to animate the controller settings or the objects themselves. They'll both work in the end based on where the object is in terms of the controlling object, which here is the empty. I'll choose to animate the empty and we'll stick with the x-axis. First, switch to the animation tab so we can see things better and animate the empty from left to right of the object. Move the empty to the left, add a single keyframe for the X location, then move the time to, for example, 24 frames, and the empty to the right of the object, then add a single keyframe there. My animation's frame rate is usually 24 frames per second, so I have a 1 second animation now. Time to apply it to something. For this video, we'll only deal with the cloth modifier, but you can choose displacement, mask, or whatever uses vertex group control. When you add the cloth modifier, make sure it's always below the geometry nodes so it reads the resulting pin group we created. And also make sure your animation is on the first frame so you don't freeze or crash Blender. Go to the physics tab and add a cloth simulation to your object. The first thing I do is scroll down to the shape toggle and add the pin group. I like to lower the stiffness to 0. It just gives a sharper transition between pinned and unpinned points. I then reduce the shrinking factor to about -0.2 and add some pressure. About 5 is fine. That will all depend on the scale of your object, but for what we have created, this will work. Let's check the animation, then deal with the rest of the cloth settings. The first thing you'll notice is the animation inflates, then deflates when the empty passes. That means we have the opposite of what we need. Let's utilize our flip switch and replay the animation. Perfect, except for some issues with collision. Let's remove object collision for this since we don't have any object collisions and activate self-collision instead. Reduce the distance to 0.001 meter for sensitive collision detection. I'll also fix my initial pin to the inner edges of the icosphere and make sure the subdivision surface is set to Catmull-Clark for a smoother cloth simulation. You can also lower the shrinking factor to something like -0.4 and increase the pressure to 10 for a puffier look. I edited the animation to be 2 seconds by moving the second keyframe to 48 frames. And that's it for linear. So on to the spherical field. The spherical field shares many properties with the linear field, meaning we can save time by duplicating what we have, adjusting it, then adding the extras we need for a spherical range. Start by deactivating the cloth modifier by clicking the computer screen on it, then hide the animated empty as we'll add a new one for the spherical animation. I chose a single arrow to represent the center. In the spherical field, the controller's purpose isn't controlling the animation, but rather generating a center point for the spherical animation. So let's rename the input to center and choose the new empty as input. Feel free to rename the empty so it's easier to tell them apart. Let's remove the access switch, groups, and the access input. And we can remove the second object info node, the self object node, and the vector math node, but keep the position node. For a sphere, we only need a central point and its distance to each of the points on the object, meaning we should add a distance math node and connect the empty's location and position node to its inputs. Then connect its output value to the A socket of each of the greater than and less than nodes. The B value will be the specified distance. What we're essentially saying is to check the distance between the center of empty and each point, and if the value is greater than or less than the specified distance based on switch statement, then select those points. So let's connect the B socket to a new input we'll call radius. Turn on the viewer node so we can check our work. Now increase the radius and see how the shape transitions to white. Mine started to show results closer to a radius of 1 because of my icosphere size. It'll change depending on your object size. And because we've duplicated our hard work, we don't even need to play with the pin group or select it in the modifier's output. Let's jump to animation. For spherical, we only need to animate the radius. Let's go back to the animation tab on frame 1, add a keyframe with a value of 0.75, then at 48, add a keyframe with a value of 1.5. Return to the first frame, activate the cloth modifier, then play the animation. If your object inflates before you reach the radius, uncheck the flip. This will also work if you animate the object or multiple objects randomly, where each object will inflate once it reaches the sphere's edges. Flipping the field will give different results whether you want those objects to inflate on entering or exiting the sphere. And now time for the final field type, randomness. Random should be the easiest in my opinion, but let's also duplicate our last geometry node tree for simplicity's sake, and deactivate the cloth modifier until we're sure everything is working fine. Let's remove the nodes we don't need, the greater than, less than, and distance nodes, as well as the object info and the position node, as randomness won't need an empty or each point's position, meaning we also need to remove the group input, center, and radius. Randomness is easiest because it relies on a noise texture. Wherever it's black, there is no pin, and wherever it's white, the point is pinned. To start, let's add a 4D noise texture so we can move the noise texture with the W value, add the W socket as a group input, and call it evolution. And naturally, we should add the scale as input so we can control the size based on the object. That covers most of what we need, but now we'll have to adjust the result that we'll output to the vertex group. If you preview the noise texture using the viewer node, you'll find that what we have has a lot of gray in it. When pinning points on an object, the grayscale value should be rounded up or down. Otherwise, you'll find that the cloth simulation won't inflate the object well. Before we do that though, decrease the scale value to about 0.5 so we have larger inflated and pinned areas. Then connect the factor to either a map range or a color ramp node. Color ramp won't allow for much control unless you use drivers, but I've never tried drivers with assets before, so let's stick with a map range node for now. Set the map range to a stepped linear interpolation and set the steps to 1. This will give you very similar results to the constant interpolation on the color ramp node. Change the from min value and notice what happens. The amount of white and black changes. This could help us control how much pinning we want on our object. So let's add it as an input and call it factor. You might have also noticed that the object turns completely white at a value of -0.5 and completely black at 0.5. So let's remap that to a value from 0 to 1 for easier use later. To do that, let's use another map range node, set the from min to 0 and from max to 1, and the two values to -0.5 and 0.5. This means if someone sets the factor value to 0, it'll set it to -0.5, and 1 should result in 0.5. To make sure you won't go beyond 0 and 1 when you drag the factor value, we should set the min and max values on the group socket settings. This won't prevent going over or under by typing a value, but most people scrub the values in Blender. Because we've implemented the flip check in the other node trees, let's implement it for the random field. All we need to do is subtract the result from 1, giving us the opposite values. Now connect the map range to the false value of the switch node and the subtracting results to the true value. What's cool about this is that you can animate the evolution to move the inflation or animate the factor to add and remove pins from the cloth simulation. You can also animate the pressure value and the shrinking factor for a smoother animation. Reset the animation, reactivate the cloth modifier, and play the animation. And now that we're done with creating the fields, let's move on to lighting, texturing, and rendering. I enjoy modeling and animating, but my favorite part has to be setting up the scene and adding color. I've been experimenting with lighting this year using more area lights than usual, but I still prefer HDRIs. I have a Studio Light HDRI, and in most of the examples, I added one strong area light to add a beam near the objects. For this example, we'll stick with the Studio HDRI, and I set up the camera to the front view for the random field setup. If you are texturing the linear or the spherical fields, I would set the camera to top view unless you change the settings on the linear to the z-axis. For texturing, we'll add one more output to all the geometry node trees we created that will act as a mask to separate the inflated and pinned sections. We need a very simple mask, so we'll only include the resulting vertex group before adding the initial pin to avoid all of these artifacts that we don't need in the texture. Add the switch result as a new group output and call it color. Then change its type to color. Now go to the Object Data Properties tab and add a new color attribute under the Color Attributes toggle. Keep all the settings as is and rename it if you like, but I kept the name as color. In the Modifiers tab, choose the color attribute in the color dropdown under Output Attributes of the Geometry Nodes modifier. On the shading workspace, add a new material, then add an attribute node and type the name of the color attribute you chose. Ours is called color case sensitive. Preview the color of this attribute and you should get the black and white mask. To apply the mask to the shaders, use a mix shader node, duplicate the principled BSDF shader, connect the mask to the mix shaders factor, and connect each of the principled BSDFs to each of the shader inputs. Then connect the mix shaders output to the surface socket on the materials output. You can create whatever materials you like and attach their results to the mix shader instead of just principled BSDF. And for a smoother look, feel free to add a subdivision surface modifier after the cloth modifier. Now on to the bonus examples and further instructions on what to do with this. I took the time to create multiple examples, so let's talk about them. For these pillows on the conveyor belt, I animated the objects themselves, and once they pass the empty or the threshold, they inflate. For this pillow, I strategically created the topology in a way that I can pin into a flower, so it inflates into a flower pillow. And I used the linear field, moving the empty through the pillow so it inflates. You can also use the spherical field here because it's circular and so it'll look nice, inflating from the center outward or the opposite. And for the rocks, because a lot of people do this on YouTube and Instagram when it comes to 3D, and it is inflating a very rigid object into something very soft and pillowy. So I made this animation just to show you that it is doable in Blender as well, especially with the power of geometry nodes. You can do much more than you used to do before. And it is using a spherical field that its radius increases, and once it meets those stones, then they inflate. And I made sure that the topology looked good enough in the inflation, because it wouldn't really matter when they're looking like stones, but it would matter when you inflate them. So that's also another thing that you have to think about when it comes to inflating objects that don't necessarily look like what you want them to look like later when they inflate. But for the example right after, you can see that it didn't really matter as much because they're both soft, but when they inflated, because all of the pins went away, they started to jump around. So when it comes to something like that, you don't have to think about the difference between your initial object and the inflated object. As for this third spherical example, I made sure that the field stays put and animated the object in and out of the field to show you how you can also use the fields in more creative ways. So you don't have to just inflate something from the center outward, but you can move something in and out of the sphere, and it doesn't have to be something that looks like a sphere. The random examples I've included and explained about them a little bit. They use the same field, but they have differently animated components. So for the first one, I animated the evolution, as in the W value. And for the second one, I animated the factor, how much of the object is pinned and how much of it is not pinned. You can also move the objects in and out of the random field, and you can get really interesting results that way. As I mentioned before, this doesn't work solely with the cloth modifier, but with any modifier that allows the use of vertex group control. I have the example using the displacement modifier. I animated the pair instead of the empty, so the pair changes texture as it passes the threshold I set. You can also use it with the mask modifier to hide parts of the mesh. And there are probably other ways that you can apply these fields to your object. I know it took so long to create this video, but I hope you learned a few new things from it. I have so much more to show you in Blender, so stay close. Talk to you soon. Bye.